Hello and welcome to session 24 of the summer math review as we get ready for school this fall. I'm continuing to cover material in pre-algebra, which would be a perfect primer for anyone heading into Algebra 1 or geometry, or maybe you did finish one of those classes, but you still need to finish the end of course exam. So those are what we are getting ready for. And today we're working through understanding the Pythagorean Theorem. Okay. So I'll wait one more minute for anyone to jump on. If you haven't already, go ahead and head over to floridamathlive.com. That is the new location where we're broadcasting the actual document camera, so you can see what we're working on. It makes a little bit of a cleaner interface, a bit easier to communicate with each other as well. Wait for a few more seconds. Okay, let's get started. So, understanding the Pythagorean theorem, right triangle is a triangle that contains one right angle. That's the one here at C, labeled with a little box. That's a right angle. The side opposite the right angle is called the hypotenuse. The other sides of the triangle are called legs. You have a short leg here and a long leg, and the longest of the three, the one that's opposite the right angle, is the hypotenuse. Okay, so the Greek mathematician Pythagoras discovered a unique relationship that exists among the lengths of the sides of a right triangle, and that relationship is known as the Pythagorean theorem. So the Pythagorean theorem states that if a triangle is a right triangle with legs of length A and B and a hypotenuse of length C, then there's a relationship that exists where A squared plus B squared equals C squared. And this next example models what that ends up looking like. So we can see this model below to verify the Pythagorean theorem. The number of square units on each side of the triangle represents the square of the length of that side of the triangle. So count the squares to verify that the sum of the unit squares on the legs is equal to the number of unit squares on the hypotenuse. So if we were to do that, so if we have, let's look at the left side first. If this left leg, this smaller leg, has a length of 3, if we square 3, we get 9, right? 3 times 3 is 9. So let's verify that here. So 3 squared is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've essentially created a square with a side length of 3. We did the same with the 4. So if we had this dimension of 4 along the bottom here, square 4, you get 16. If you count all these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And it checks out, right? Now, what's interesting here is we have a 5 on the hypotenuse. And if we were to add these two together, add 4 squared, let's add count all of the, so we have a 9 over here. Count all of those unit boxes. We had 16 over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 over here. And over here, we will find, we're going to do the 3 squared equals 9. 4 squared equals 16. And if we were to count all of these up, it should be a total number of boxes of 9 plus 16, or 25 boxes. Let's go ahead and verify that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, so it works out. And 25 is 5 squared, right? So 5 squared equals 25. Can we get the 5 from the length of the hypotenuse there? So let us know if you have any questions. You can put them in the comments either on the behind the scenes live stream on Facebook or through floridamathllive.com. You can put it in the bottom of the interface on floridamathllive.com. Okay, so let's move on to more material here. Keep working on our lesson on Pythagorean theorem. Okay, so when you reverse the parts of an if-then statement, the new statement is called the converse of the original statement. Here is the converse of the Pythagorean theorem. So converse of the Pythagorean theorem, if a triangle has side length A and B with the longest side of length C, then we will have this relationship. Then the triangle is a right triangle. So essentially what we're doing is if we take one leg A and square it, take the other leg B, square it, add them together. If those do indeed match C squared, then we do have a right triangle. So let's check here, follow these steps down here if we have a right triangle, okay? So first identify A, B, and C. So our legs would be A and B, or A and B. That part doesn't matter as long as you distinguish, make a distinction between the legs and the hypotenuse. So they assigned A to be 5 and B to be 12. So we want to check if A squared added to B squared, if that matches C squared. Okay, so we're going to do 5 squared plus 12 squared and see if that gives us the same number as 13 squared. So you can check these out if you use a calculator or your mental math. So 5 squared is 25, 12 squared is 144, 13 squared is 169. So if we added 25 and 144, and that equals 169, then we would in fact have a right triangle, and it checks out. Those two numbers on the left do add to 169, so we would have a right triangle. Let's try one more. So over here, they were kind enough to even show us a triangle that looks as if it were to be to scale. When you get to the EOC or the SAT, ACT, those types of tests, sometimes they play a mean little trick, and they'll do something like, this triangle is not to scale, and they will make it look like it is a right triangle. So if they ask, is this a right triangle? You say, it sure does look like it. So you have to actually check these numbers to verify using the rule. So the longest side here is 20. So that would be assigned C. The other two sides are 10 and 15. We're going to assign those A and B. So we want to check if squaring A and squaring B, that adds up to squaring C. So 10 squared is 100. Squaring 15 gives us 225. Squaring 20 gets us 40. So if we were to add 100 and 225 together, would that give us 400? I don't think so. 325 does not equal 400. Okay, so since 325 does not equal 400, and specifically squaring one side, 10 squared plus the other leg squared, 15 squared, that does not equal 20 squared. So this is not a right triangle. All right. Let's have another look here. Okay, so we have a word problem. The most difficult part about word problems is having the patience to actually read the question. I find many students, they see word problem, and step one is to guess, okay? That's not a great strategy, and these really aren't usually that difficult of problems. Just take your time with it, and you can figure out what they're looking for. Okay, so Mariano needs to repair a window that is 24 feet off of the ground. So a lot of times drawing a picture helps us start to understand this. So if we're talking about a window that's 24 feet off the ground, then we're probably looking at the side of a building, right? So let's draw a building, draw what we know. We know what a building looks like. We know what a window looks like. So what is that dimension? 25 feet, I'm sorry, 24 feet, yes. We even try to keep the colors consistent. So that's 24 feet. 24 feet. He wants to place a ladder 7 feet from the base of the house. So that's pretty easy to identify, right? Here, where's the base of this house or building? Base is here. And we're thinking about, so what does the ladder look like when we lean it up against the wall? We're going to lean it like this, right? And we want to make sure it's the right distance away. So maybe he has this experience at about 7 feet away from the wall is the amount that prevents him from, if it's too close to the wall, right? He'll fall back. If it's too far away from the wall, maybe it'll slide down the building. So finding that right balance of 7 feet, it says it's going to be 7 feet from the base of the building. And the ladder is 25 feet long. We want to ask, will the ladder reach the bottom of the window? I kind of drew this silly. So really we're measuring, I suppose, to this point here for 24 feet. So let's see if it will reach that distance, right? So the distance from the bottom of the window to the ground is 24 feet. And we want to see when we lean this ladder up, what is that going to look like for us? 25-foot ladder. So if it's longer than 25 feet, we have an issue, right? Because it's going to go right into the window and break the window, given this relationship in the right triangle here. If it's shorter than 25 feet, we might, if we don't meet this point here, we're either going to break the window or we're going to fall in too short, is essentially what they're asking. So will the ladder reach exactly the bottom of the window, right? If it's too low, we can't do our job. If it's too high, maybe we push up against the glass and make a problem there. So let's do 24 squared. So we're going to identify the legs and the hypotenuse. So let's do 25 feet. That's going to be our C. In terms of, I'll even write that at the top. Keep our colors nice and organized. You can see what I'm referring to. Okay, so we assign one leg this 24 feet. We assign the other leg of this 7 feet. And as you can see, the triangle that I'm looking at is this leg, and this leg. That's the triangle that we're visualizing, okay? So to make sure we get our math correctly, let's do this together. Clear that screen. So 24 times 24 is 24 squared. That's 576. Seven times 7 is 7 squared. That's going to be 49. Let's add those together while we're at it so we can simplify that side. So this side those two are going to combine to give us 625. And if we end up with 625 on the right, if 25 squared gives us 625, then we are working with a right triangle that is going to meet this criteria that we're looking for. So 25 times 25 is how you make 25 squared. And we did end up getting 625. So it checks out. It is a right triangle. And it does reach exactly the bottom of the window like we're hoping. And here's their illustration. Okay, so step one of a word problem should not be to guess, like I see so many of my students do, or try before they're corrected. The first step should be to read it. Sometimes the second and third step should be to read the problem as well. The step after that should be to try to draw what's happening. And if you can start to make those baby steps, then eventually you have enough information where you can start to make a decision on where to go. So let's work together on this example. So it looks like Taylor's building a door for a cabinet. And let me actually cover that up because we would only have this. That's all we'd have. Okay, so Taylor's building a door for a cabinet. So if you can picture what a cabinet looks like, think going in your kitchen and looking at one of those doors. The corners of the door must be right angles. Makes sense. Have a nice flush interaction between the door and the cabinet. So they must be right angles. The door itself is 7 feet tall and 2.5 feet wide. The diagonal of the door measures 7.5 feet. Is the door indeed a correct shape? Okay, so let's draw a picture of this. And I don't know why it's a kitchen. This is talking about a cabinet, maybe like an armoire or a closet. If it's 7 feet tall, I don't think I've seen anything like that in my kitchen. Okay, so we have this door. If you want to put a handle to visualize it better, that's fine. So that's our door. It is 7 feet tall. And just for fun, let me go ahead and label this side as well. That's also 7 feet. They're telling us it's 2.5 feet wide. And the diagonal would be from one corner to the opposite corner is 7.5. So what we're doing is we're checking if this is right angles because it's asking us if we do actually have right angles. So what we're doing is, let me actually do one of these that symbolizes a right angle. And maybe put a question mark because that's ultimately what the question is asking. If these are, oh gosh, right angles, okay? So how do we do that? So I wanted to just show that the bottom dimensions, get in the practice of, it says it's 2.5 feet wide. It's also 2.5 feet wide up here, 7 feet tall. That side is 7 feet tall. So to maybe cover up any confusion, if there is any, let me cover up one of these triangles to show you kind of what we are looking at. So let's just look at what we see there as a triangle. We're going to use the Pythagorean Theorem. 2.5 squared plus 7 squared equals, and let me do that equals question mark, right? Because that's actually what we are testing. Does it equal 7.5 squared? I'll definitely need a calculator for this one. Okay, 2.5 times 2.5. I know there's a square button on here as well, but sometimes I like to illustrate how to do something squared if you're using a calculator that doesn't have a squared button. Okay, so 2.5 times 2.5 gives us 6.25. Plus 7 squared, we know that's 49. And 7.5 times 7.5 gives us 56.25. Do that in blue. I'm going to bring down a question mark. That's what we're testing, if those are indeed equal. So let's go ahead and add 6.25 and 49. So 49 plus, getting my pens, maybe we'll just do this one in black over here, 55.25. Does that equal 56.25? We would say no. So what does that mean? That means that we go back to the definition back here. So using the converse of the Pythagorean theorem, it states that if a squared plus b squared equals c squared, then it's a right triangle. So we ask ourselves over here, does a squared plus b squared equal c squared? We got no. So what that means is we would say, then it is not a right triangle. Not a right triangle. Okay. So it's not the correct shape because it demanded that the angles of the doors, they need to be right angles, and that's simply not the case. Okay, let us know if you have any questions in the comments. I can go deeper into one of these examples, or we can answer any questions that you're working on for summer school. School is indeed right around the corner, and it's best to start ahead of the game instead of starting behind. So well done if you're watching this now. Awesome. Okay, I'm going to leave this one here for just a moment. I'll let you think about that and see if you can think of how we would work on example 5. So let me leave that here for a minute, and we'll look at that together momentarily. Okay, have you had a chance to look at that one? So let's work on example 5 together. So in this case, it's asking us to find x. So we need to assign these legs a letter. Okay, so first it's best to identify the hypotenuse, and in this case, the longest side, the leg that is opposite of the right angle is the hypotenuse, and that's going to be our c squared. And we're looking at a squared plus b squared equals c squared. So a, let's assign that the x. So we're substituting each a, b, and c for the legs of our triangle. So this is going to be 35 squared equals 37 squared. So we're no longer checking if this is a right triangle. They are telling us it's a right triangle because of the little square in this angle here. Okay, so they're telling us it's a right triangle, and we need to solve for x. So let's see what 35 squared gives us. It's 1225. $37 squared is 1369. And over here, x squared is just x still, okay? So let's solve for x. Let's subtract this 1225 on both sides. Gives us 144. So x squared equals 144. So we want to know what x is, not what x squared is. So how do we get rid of this squared? What is the opposite of squaring, or the inverse of squaring would be square rooting, right? So if we took the square root of both sides, that would cancel, and we'd simply have an x over here. Now, when you do take the square root of something, really what you end up having is plus or minus whatever that number is, which is 12. And how that works, if it's plus or minus, now mathematically it is plus or minus, but in the real world it is it can't be a negative dimension. A negative dimension simply doesn't make sense. So it would have to be the positive version of x equals 12. Okay. So I went a little bit more in depth in this property here. Let me just show you what I mean, because not only does 12 times 12 get us to 144, but let's find a negative. Wrong thing. It's been a little while since I used this calculator. Looking for the negative button. Let's do it on paper. It'll be better anyway. So if we do negative 12 times negative 12, and if we were to factor out this negative, really what we have is negative 1 times 12, and over here times negative 1 times 12. I can reorder these. Negative 1 times negative 1 times 12 times 12. Negative 1 times negative 1, they cancel to become really a positive 1. So what's 1 times 12 times 12 gets us back to the 144. So that's why when you take the square root of something, there's a plus and a positive and a negative solution. But using common sense, if we're dealing with dimensions, at least in our real world, you can't have negative measures, right? Okay. Give you a second to look at that solution, and definitely go ahead and post your questions into the comments if you have any questions about this material or anything else that you might be covering in another class, if you're studying for another exam or certification. I can help try to answer that as well. Okay. All right, so let's try this next example together. Example 6. A lot of good examples in this one. I like geometry. All right, so a baseball diamond is a square with sides measuring 90 feet. Okay, this side is 90 feet, that side is 90 feet, this side is 90 feet, and that side is 90 feet. You can picture a baseball diamond. Maybe there's a batter and a catcher and an umpire down here. Field extends around here. We're talking about a baseball diamond. So what is the straight line distance across the diamond from the first base to third base? So I'm not sure why we would necessarily need this. Maybe we were just doing having a conversation and betting a friend whether it's shorter to go from first to third or first to second. I don't know. But we wanted to see what the distance between those is, right? Or maybe we're talking about how long does the ball get thrown if there's a double play from someone, a catcher catching the ball, or a first baseman getting the out here and then throwing to third base to try to tag someone out. Maybe it's how far is the ball traveling across the field, not counting the arc that it goes through. So what we're doing is we only need to look at one of these one half of this square up here. And this spot here is our C that we're looking for. That's our hypotenuse. And our A might be over here at 90, and our B is over here, also 90. So if we do that, then A squared plus B squared equals C squared. 90 squared plus 90 squared equals C squared. So let's work on that. 90 times 90, 8100. So those are both 8100. Equals C squared. Add those together. 16,200 equals C squared. So now we need to get rid of this squared term here. And remember, we can square root both sides, and we would just have C left over here. And do square root of 16,200, sorry. And we get 90 root 2, or let's force that to give us a decimal number. I think that'll do it. So 127.3. And of course, that would be plus or minus. But since we're talking about dimensions, we would only take the positive version of that. Okay. Hey, they got the same thing. What do you know? Okay, what do you think? Have time for one more example? Let's actually do this one over here. Go ahead and get your questions posted now if you do have any. Happy to help you with those. So let's work through 7. Let me give you a second to think about that. So think about what the strategy would be. We probably, since this whole section is labeled Pythagorean Theorem, probably have something to do with that. So think about that for one more minute, and then we'll do that one together. Okay, so let's go ahead and start to label our A and B and C, all right? So remember, the Pythagorean theorem is dealing with right triangles. So we need to identify, when we drop a line from the top, I know we're dealing with a cone here, so you may be tempted, maybe you thought about a formula for a cone, but you don't actually need that because we're looking at from the top of the cone down to the center and then over to the edge over here. So 20 is going to be our C. It'll probably be easy to identify one of our legs, right? So again, if we look at it, that this hypotenuse is opposite of the right angle, and that's C is 20 in this case. It may be easy to identify one of our legs. So A is H, so we're trying to find H. Different color here. It's always fun. Okay, so our A is H. So what is B? So it may be tempting to say, oh, B is 24. But be careful, because ultimately what we want is, if this is the leg for the hypotenuse, and that's C, and this leg are H and A leg, then it would make sense that the segment joining this other end of the hypotenuse to this end of this leg is going to be B, correct? So when we start to think about it and sometimes draw a picture, it really helps us out. So this section here is going to be our B. So one of the properties, if we drop a line from the top of a cone like this, it's going to hit right in the middle of the base of this cone. So if this whole distance is 12, then half, did I just say 12? If this whole distance is 24, then half of that distance is, guess it would be 12, right? Kind of give you the answer early on that one. So let's go ahead and plug these in. So if H is our A, so I'm going to plug in H where A used to be in our formula. Our B is a measure of 12. B squared, 12 squared. Our C they give us is 20. And that, whatever that is, we plugged in, squared. So let's go ahead and start to solve these. So H squared is going to stay H squared. 12 squared becomes 144. Zoom in a little bit. 20 squared becomes 400. Now we subtract, right? We're going to subtract 144 on both sides. Just like that. We're going to get 256. So H squared equals 256. Oh my gosh, what did I do that for? Let's just rewrite that line. H squared. I think I wanted to put an exponent over there for some reason. 256. Okay, now we need to figure out, we don't want to know what H squared is, we want to know what h is. So let's take the square root of that 256. And we get 16, as you can see. So if we take the square root of both sides, that's going to cancel the squared. We get h equals 16. Okay, we leave that up there for just a moment. Please go ahead and post any questions you have. Again, going forward, we're going to be doing, if you want to see what we're writing here, seeing what the lesson is writing, we made a new interface that's a little bit cleaner to interact with. If you go to FloridaMathLive.com, FloridaMathLive.com, and just jump on in there. It makes a nice interface for us to communicate on. You can post your questions in the feed here, or you can go to FloridaMathLive.com and post them in the feed there. If you have a question about what we covered tonight, or anything we've covered this past week, anything you're covering in summer school, or if you're studying for maybe you're retaking the OC test, studying for a SAT exam, anything like that, you can post those here as well, and we'll give a crack at it, see if we can figure it out together. All right, everyone, I will stay on for just about 2 more minutes. See if you have any questions. Again, thank you for liking and sharing with those that may benefit from these free classes this summer. So we'll stay on for 1 more minute. So tomorrow, we're going to be going over finding distance between 2 points on a coordinate plane. Hey, that looks familiar. It looks like something that we just learned using the Pythagorean Theorem. That's exciting. Everything in math builds on itself. And that's why we're doing pre-algebra this summer, so we can get ready for algebra and geometry this fall. Okay. So again, today we just finished understanding the Pythagorean Theorem, and looks like we finished up with any questions that were coming in. All right. Thank you very much, everyone. This is Wilson with Florida Math Exam. Have a great evening.